log in from another account as well for the camera.
Achha, theek hai. Okay, sure.
All right. So hopefully everyone can hear fine.
Yes.
During the talk, please, if at any point you have questions, feel free to just shout out or put something in the chat, and I'll try to answer the queries to the best of my ability. Much better that I answer queries so that you understand stuff rather than I complete whatever I plan on completing. So if you noted the abstract that I sent for the talk, I kind of identified two very disjoint kind of talk contents, one regarding contextuality and one non-locality. Initially, I had planned to kind of talk briefly about both of them, and then I thought, hey, it's much better to talk kind of in some reasonable details so that everyone feels they got kind of a good understanding of the problem involved. If time permits, I will still continue on to the second problem, but I will focus my time more on one specific problem. And as the title implies, I'm kind of going to be talking about partial progress towards kind of an open problem related to one of those topics. So what I'm going to focus on is a problem that I've been interested in non-locality for a while. And the work is joint work in progress with Peter Hoyer at University of Calgary and Amin Shiraz-Gilani, who was initially with me at IBA, and now he is at University of Maryland pursuing his grad studies. All right. So I won't assume any prior knowledge about non-locality, and we'll kind of move from scratch. But if you know there is something that you feel I'm already assuming that you know and you don't know, please just let me know. There are some technical details towards the later end of the talk, which I will kind of say, hey, talk to me outside of the session if you're interested in those details. Okay. So before I'm able to express the statement of the problem, let's say the framework that I'll be working in. And given that I'm a computer scientist by training, and that's the cool thing about quantum information, wannabe physicists like me who only know CS can also talk about quantum stuff. So we'll be looking at non-locality and the model of cooperative games played by players or entities. So the framework that you can have in mind at the beginning is that we've got, let's say, two parties, usually labeled Alice and Bob. Alice and Bob will receive an input bit X and Y respectively, and they're supposed to output a bit A and B respectively as well. And we can assume if they're classical players that if the laws governing whatever they'll be able to do in their lab is governed by classical physics, then yes, they might have some shade randomness, which is represented by this lambda with these dotted lines. What do those dotted lines represent? The idea is that Alice and Bob might have met at some point to discuss, create this shade information, shade variable that they have between them. But after that communication among them, when kind of the game is about to start, they are sent to their own booth. So you can have a game show kind of visualization of this framework as well. Alice goes to her booth, Bob goes to his booth, and the doors are closed, essentially signifying that once the game starts, there is no longer any communication allowed between Alice and Bob. And so that kind of makes things interesting, because now what we end up implementing, because of no communication between Alice and Bob, is that Bob will not know the inputs Alice has received, and Alice similarly will not know the input string or input bit Y that Bob has received. And so that makes things interesting in terms of how we can make interesting games out of this. And to begin with, the game that we'll set up is governed by this rule. So the parity of the outputs, and this is just a logical parity, quick refresher. So if you got A and B as 2 bits, A parity B or A XOR B is just this truth table. 0, 1, 1, 0. And similarly, AND of X and Y. So that's just when both the bits are 1, the output will be 1, otherwise it will be 0 for the remaining 3 inputs. And so this is the constraint that Alice and Bob need to satisfy on the output bits they produce, conditioned on the input bits that they receive. Any questions about the setup? This is something that we'll keep coming back to again and again in our following slides. And one way to visualize or to think about, hey, what's the space of different strategies or different results that Alice and Bob can produce is really just this 4x4 matrix of 4 probability vectors, where each row can be thought of as a probability vector. You can assume that the rows are indexed by the input bits X and Y, and the columns are indexed by the output bits A and B, so that each entry is essentially a probability P of AB condition on X and Y. And so for each row, X and Y is fixed, so each row is a conditional probability vector, right? And the red and green coloring over here signifies that if we can consider this rule, A parity B equals X and Y, you know what's the interesting thing that's happening over here, right? So exactly for all these red entries, the condition of A parity B equals X and Y is not satisfied. And for all these green entries, the condition is satisfied. So ideally, what Alice and Bob would like is to get non-zero probabilities only on these green entries and zero probability on the red entries, right? What we want to see is whether or not that's possible or not. If that's possible, then they'll always win the game. Now, you could consider a trivial strategy where Alice and Bob really just say, hey, let's just always output 0, 0. You know, don't worry about any interesting randomness or whatnot. And just by looking at this matrix, you can see that, hey, in 3 of the 4 possible inputs, they end up then satisfying the winning condition for this game. But then this 4th interesting row where, you know, the kind of the winning and losing conditions are flipped because and is now 1, they end up losing in this setup, right? And you could now, there's a nice simple proof to argue how any classical strategy, in fact, will be bounded by this bound or this limit. And one way to kind of nice way to see it is to think about writing this down as AX and BY, where AX represents the output of Alice on input X, B sub Y represents the output of Bob on input Y. And so you write down the 4 conditions. You want A naught parity B naught to be equal to, well, X and Y. Well, X and Y in this case is 0, 0. So you want 0, 0, 0, 0 and 0 to 0. Same thing will happen for A naught parity B1. Same thing will happen for A1 parity B naught. You get 0 in all these 3 cases. However, for the 4th case, A1 parity B1, you want this to be equal to 1. Right, so we want to simultaneously satisfy these 4 conditions, and you could literally just sum up these 4 constraints. And now you realize that by just simple logic rules, A naught parity A naught. So assume I'm just taking the parity of the left-hand side and taking the parity on the right-hand side as well. So just adding them up essentially. A naught parity A naught is 0, A1 parity A1 is 0, and similarly, B naught parity B naught is 0, and so on and so forth, so that the left-hand side will essentially just evaluate to 0. Oops. So if I were to take the sum of all the 4 entries on expressions on the left-hand side, I get a 0. But the expression on the right-hand side, or the entries on the right-hand side, give me a 1. And so obviously 0 is not equal to 1. I get a logical contradiction. And so you get this idea that, hey, there is no satisfying assignment to all of these 4 constraints or to these 4 variables, A naught, A1, B naught, B1, such that I always win the game, right? And that in itself, that statement is really just an expression, or can be restated as what historically is known as a Bell inequality, right? So this research agenda essentially is going back to 1935, where EPR in their 1935 paper are asking, is quantum mechanics complete? And 1969, John Bell comes along and says, derives what are called Bell inequalities. The inequality that we've just looked at is what's called the CHSH inequality, slightly after Bell's original result, which is essentially saying, hey, if I sum up all the probabilities of Alice and Bob winning and subtract from it the sum of all the probabilities for which, for the events in which Alice and Bob lose the game, then that is going to be bounded by 2. And we can verify that this is saturated for the trivial strategy that we looked at. Always output 0, 0 will give you 3 for the first 3 rows, and 1 or minus 1 from here for the 4th row. So you'll get 3 minus 1 equal to 2. And we've just seen that it's not possible to get anything better. And it's a trivial argument to show how a probabilistic strategy can't do better than a deterministic strategy. All right, so we've got something along the form of a Bell inequality. It's interesting because, well, because we're interested in quantum information and without going into the actual derivation of the details, if Alice and Bob were to share an entangled state rather than just classical shade randomness, then we do know that Alice and Bob can violate this previous inequality. So rather than getting a bound of 2, they can actually get a value of 2 square root of 2, right? And this can be saturated as well. So there exists, if Alice and Bob were to share just the maximally entangled state, EPR state, and then perform some reasonable measurements just in the X and Z basis, or a superposition thereof, they're able to saturate this inequality. Now, what's interesting though is if you just look at the format of this expression, 2 square root 2 is not actually the mathematical maximum of this expression, right? Anyone care to write down the mathematical maximum of this expression in the chat or shout it out? So if I just look at this expression in the middle, what's the maximum value it can take? So just consider that this expression is a sum of probabilities, this expression is a sum of probabilities, and we are essentially just summing over all the winning events, which are these, and the losing events, which are these marked in red. And all these 16 events are really just coming from 4 probability vectors. So imagine if there was a strategy that were to win in all possible input cases, and I sum over those 4 probabilities, then what would this expression give me? Not a trick question. Venture a random guess, perhaps? If I've got 4 probability vectors and each of them, let's say, let's assume there exists a vector that can actually assign 1, 1, 1, 1 to each of these 4 entries, then I would get actually the maximum of 4 over here. Everything is saturated, so there will be 0 contribution from the negative expression. And so the maximum possible mathematical value for this expression is actually 4. And one question that you can then ask is, just like quantum information or access to shade entanglement allowed Alice and Bob to get something stronger than what was allowed classically, is it perhaps possible that there exists an extension of quantum mechanics that allows you to go beyond 2 square root 2? Or another way to ask the same question is to say, hey, what are the principles? What are the what are the first ground principles based on which we can conclude that this has to be the bound? What goes wrong if there is a physical theory that allows me to get something up beyond this? Right, and so that's been kind of a research agenda for nearly kind of 2 decades to figure out that even though there exist these quantum correlations that are stronger than classical correlations, but since there exists a possibility for this expression to take the value 4, is it really possible for a physical theory to allow that maximum possible value of 4? And what are the consequences of such a physical theory if it would actually allow for 4? Could we actually derive such a physical theory? Right? And so what we then consider then is what are called no-signaling constraints. So what are no-signaling constraints? No-signaling constraints is us essentially trying to enforce what are the constraints or what is the motivation of our constraints in this original framework of the game. In the original framework of the game, we said Alice should not know Bob's input and Bob should not know Alice's input. So we are allowing now Alice and Bob to share some hypothetical resource as long as that resource does not allow for signaling to happen between Alice and Bob. What kind of constraint should that resource satisfy? And so here's one way we can visualize or kind of write it out. So we can consider Alice's marginal probability of A condition on X. And similarly, we can consider Bob's marginal probability to output B on input Y. Right? By definition, this is really just summing over all of, Bob's output for some fixed input XY. Right? That's the definition of Bob's marginal. So given that we have access to that 4x4 matrix in terms of these probabilities P of AB given XY, for a fixed XY, I just sum over the B's and I get this marginal of Alice out. Similarly, I could do the same thing for Bob as well. Now, what the no-ceiling constraint actually says is this marginal is essentially the data, the statistics that Alice can see on her end of the lab. She has no communication from the outside world, in particular from Bob. So this statistical measure or this distribution should not be influenced by the value of Y. And that's what we want to enforce. So what Alice is able to see in her lab, what Alice is able to produce in her lab should not be influenced by whether Y takes the value 0 or whether Y takes the value 1. And so we can write this down then. So the initial part in black is the definition, where now the additional blue part is the constraint. That the marginal should then equal P of AB given X, Y prime. So if Y was 0, I'm taking Y prime to be the complement. It will be 1 and vice versa. Similarly for Bob's end, sigma A, P, A, B, condition on X prime, Y. So these constraints enforce that both Alice and Bob's local worldview, which is essentially their marginal, is uninfluenced. There is no kind of experimental procedure that Alice and Bob could do because their probability distribution on their output remains unchanged, regardless of how Bob's input changes or Alice's input changes, right? So this then intuitively is enforcing the constraint that we did apply on this game. And so now we ask, what are the kind of boxes, the boxes that we label as N in the beginning? What are the kind of four matrices that satisfy these no-ceiling constraints? And in particular, one of the surprising conclusions that one can draw is that we can now find a satisfying assignment to this 4x4 matrix, which satisfies the no-ceiling constraints, while at the same time giving me the maximum possible value of 4 of this expression. And that's really just me applying a uniform distribution to all of the 8 winning events. So I'll leave it as a nice exercise for you to verify that these constraints are satisfied by this matrix, right? And so one is led to the question that if this box, which is called the non-local box in the literature, so you say, hey, there's this hypothetical box that Alice and Bob share, just like Alice and Bob share an entangled state or shared randomness. There's this hypothetical box that Alice and Bob are able to share. Alice inputs her bit, Bob inputs his bit on his end, and out comes this A and B, which Alice and Bob will directly output as well. And the rules of how the box itself works guarantee that the condition of the game is always going to be satisfied, while at the same time also this box by definition generates statistics which do not violate the no-ceiling constraints, and hence there is no signaling happening between Alice and Bob. So how do we understand this situation, right? So we've got kind of a 3-layered setup over here now. First, there was the classical world, which got us the value of 2. Then there was this quantum world, which gave the value of 2 square root of 2. But then if you said, hey, let's just consider the experimental setup I had and the main constraint I had on the setup of no communication happening between Alice and Bob, then I'm still getting something strictly larger than what's allowed by quantum. How do I understand this gap? And that's essentially the problem that we want to explore, or I want to explore. So one way to kind of consider, one thing to consider is what would be the consequences of a world in which these boxes are actually physically realizable, right? So we just showed that they don't violate the no-ceiling constraints. So, Alice and Bob are not getting some kind of superpower of being able to communicate superluminally by having access to these boxes. These boxes are tame in that sense. No signaling condition is satisfied. But are there some other consequences which are non-trivial of these boxes? So I'll introduce one task for which these boxes are indeed very useful. So we modify our original problem to say, rather than Alice and Bob playing the game where they want to produce A parity B equals X and Y, let's actually make it a bit more general task. Alice and Bob want to produce output bits A and B such that the parity of the output bits A and B equals some function over bit strings X and Y. So there's a bunch of generalization that I'm doing over here now, right? Originally in our setup, this X and Y were just a single bit, whereas now with this X hat and Y hat, I'm considering these to be some length n bit strings. And this F is a Boolean function defined on this length 2n bit string. And then the task we are considering is what's called computing or distributed computation of a function. Alice and Bob compute bits A and B such that the parity of those two bits equals a function f of x hat y. So our previous game was just a special case of this setup where we had just a single x and a single y, and f was the and function, right, as mentioned over here. But now we are making it a bit more generic task, including that Alice and Bob could get multiple length strings. Now, it shouldn't take too much of thought to convince yourself that for a reasonably defined function f, Alice and Bob would need to communicate with each other in order to satisfy this constraint. Imagine, for example, Alice and Bob share a recently downloaded, 4K version of some video, and they want to compare their local downloaded files, whether or not they are the same or not. It's a non-trivial expectation to believe that they would be able to match each bit of the downloaded data. So Alice has her version of, some 10 gigabyte file. Bob has his version of his 10 gigabyte file. And they want to check, are all the bits in my downloaded version exactly the same? A special case of it is being what I'm working out over here. Alice and Bob want to check or compute the equal function. Alice has 2 bits, x1 and x2. Bob has 2 bits, y1 and y2. And they want to evaluate the function equal on this. Equal, based on the truth table mentioned over here, will evaluate to 1 if and only if x1 equals y1 and x2 equals y2, right? So that's one condition, that's another condition, that's the third, and that's the fourth condition, in which these are the 4 cases in which the equal condition or would be satisfied, or equal should evaluate to 1. People with me? Questions, queries, concerns? So
if you have questions, you can ask this to all students. You can just raise your hand and ask. I'll mute. Yeah, you can ask questions. Yeah.
So if you've been following along, the next argument is really nice and simple, which gives away the strength of what these non-local boxes are capable of. So assuming we can convince ourselves that this truth table can be represented as this sum of product representation, right? So you take the 4 rows for which the function evaluates to 1, write it out, simplify, and we get this expression over here. Now we make the following observation. Let's call this entire expression. You note that this entire expression is actually only dependent on Alice's inputs, right? So this is something Alice can compute locally on her part. So let's label it as x prime. Parity. This thing is now local to Bob, y1, y2. Bob has access to these 2 input bits on his part. So let's call that y prime. Parity. Now here comes kind of a non-local and. In non-local in the sense that Alice and Bob can't really compute it locally because there's an and happening over here. But this and can exactly be computed by application of this rule. If Alice sets 1 plus x2 as her input, let's say x double prime, dot, and let's say y1, and now Alice and Bob were to use a single resource of this box where x is set to x double prime, y is set to y1, then Alice and Bob will get, instead of x dot y1, out from the box, some strings a and b, or bits a and b, such that a parity b will be equal to x prime double prime dot y1. And so this and, which was not possible to compute using local resources, can be actually computed using this non-local box. And the same thing kind of happens over here again. And if you buy this argument, and if you follow this argument, then you realize that, hey, this argument actually will carry forward to any Boolean function. Because at the end of the day, we know every Boolean function will have this truth table representation. That truth table representation can always be mapped into this some product of some representation. You expand out that product of some representation to get a bunch of expressions. Some of them will be local, such as this X prime. Some of them will be non-local, as this one. It might be more complicated than this one, but the idea would be within each such product term, you would be able to write it in terms of years. Let's zoom in. Here's a bunch of stuff from Alice and it with a bunch of stuff from Bob. You take those two kind of expressions, feed them into a non-local box, and out come 2 bits that allow Alice and Bob to get rid of the and replace it with a local parity. And so you would get at the end an evaluation where Alice is able to compute some expression, parity, Bob is able to compute some expression, Alice sends this as output, Bob sends this as output, and you're guaranteed now by the computation that the parity of the two outputs will be equal to the function that they were interested in. Not just this example, but in fact for any Boolean function. And so that goes in the face of all that's known about the hardness of communication complexity. So communication complexity perhaps is not as popular as people kind of in relation to quantum computing, especially when people talk about Shor's algorithm, etc. We are usually talking about computational complexity, where you don't have to consider this spatial separation between parties, and you're just saying, hey, I want to compute this function, solve this problem, how much time will it take? So that's computational complexity. In communication complexity, we're considering, hey, there are distributed parties, and those distributed parties would like to compute some function. What's the amount of communication that would be needed between those parties? And here what we've shown is that for the two-party case, access to this hypothetical resource of a non-local box would make communication complexity trivial. So you can take any function over as large an input as you like, and using a single bit of communication, Bob will be able to output exactly the value of that function. Right? So usually when this result is presented to physicists, they're like, okay, big deal. From CS perspective, and people usually are like, yeah, this seems like a reasonably non-trivial task. So we can take this as a in principle reason in terms of why any reasonable physical theory should not allow for the physical realization of such correlations as those governed by a non-local box. Okay, so that's all known and done with. The issue though is, if you imagine the space of all possible correlations or distributions that can be written in this 4x4 matrix, then it's possible to come up with a convex polytope. Just imagine this space of boxes in which you can kind of visualize, hey, here's the space of those boxes that are allowed by classical mechanics, those originally or classical physics that were bounded by this value of 2. Then you can have this quantum bound, which allows this value of 2 square root 2. And then you've got this no signaling bound based on the no signaling conditions that we checked, which is something strictly larger than even the quantum bound. This kind of vertex, this point on the top, is exactly the non-local box that we identified over here. The argument that we've just given for trivial communication complexity shows that if you have access to this perfect non-local box, you can then end up in a world in which communication complexity is trivial. But that leaves, if you are taking that as a rule to rule out why this box is not allowed in a reasonable physical theory, it still leaves open the problem of what about this entire region above the quantum bound, which is still within the no signaling bound. What information principle disallows those correlations? And there's been lots of research on this direction. I won't go into all of them. One that we'll end up focusing on by the end, because I gave the specific example as well, is of communication complexity. So the perfect non-local box, the one without any noise, allows you to deterministically get a communication complexity of just 1 bit for any Boolean function. People have looked at the randomized version of that result, where they say, what if my non-local box is noisy? So it gives me a value above 2 square root 2, but below 4. And so people have got kind of a non-tight bound of roughly, if I recall correctly, something like 3 point something, where they say, all right, for any box above this value of 3 point something, we still live in a world where trivial communication complexity in a randomized sense will be possible. And so that still leaves open this space. And so that's the big research problem that agenda that we're interested in. What are the information principles that restrict the non-locality of quantum mechanics and quantum information to what we know as this bound? Or we can flip it around and say, could there exist a generalization of quantum information such that, if you were to take the version of an entangled state in that physical theory, you would be able to get something, let's say, that happens over here, stays over here. We know that if you are taking communication complexity as the principle, then it's already disallowing anything above this point or this line. But then we are still left with this region. So that's what we want to explore about the possibility of what information principles, what rules kind of limit the strength of non-locality in a physical world. And as I mentioned, there's lots and lots of work based on different motivation, people coming in from different backgrounds, studying what is the source of those limitations. Note that our discussion so far has been limited to bipartite non-locality, in the sense that we were only considered two parties and kind of shade entanglement between these two parties. A while ago, there was a nice result that said that if you want to actually come up with a bound on non-locality, on quantum non-locality, then what you should really be looking for are multipartite information principles and not bipartite local information principles. And the key motivation of that argument was along the lines of the fact that they said, hey, we have identified a multipartite correlation. Whenever I say correlation, imagine that box N that we had, that 4x4 box, but now it's a larger box for 3, 4, 5, 6 players maybe. And they said that this box, we have identified a box such that it is stronger than quantum for that 5-party case. But if you were to take any bipartite partition of that stronger than quantum box, any bipartite partition actually becomes classical. So it's almost as if the middle ground of quantum is kind of left with. So in the general 5-party multi-party case, you get a correlation that is stronger than quantum. But any bipartite partition of that 5-party partition becomes classical. So if you have a bipartite information principle, obviously it will satisfy this bipartite partition, even though the original multipartite distribution correlation that you have is provably stronger than quantum. So that's the argument for why, if you're going to be looking for information principles to bound non-locality, you should be looking for multipartite information principles. And so motivated by that, sorry, question?
So just wondering about this from a physical, physical implementation point of view. How can it be like physically visualized?
The audio is a bit low. I couldn't exactly make out.
Yeah. So like just trying to think about this non-local box, how would it mean in terms of physical implementation? So like you have, let's say, a certain system, qubit processing systems to bipartite systems, and then there is some interaction between those can be visualized as a non-local box.
Exactly right.
Okay.
So yeah, exactly. So if you want to realize this physically with qubits, you would need to have a direct interaction between the two qubits. And as soon as you do that, you kind of violate our kind of constraint from the setup that these two kind of the input coming from Alice's end and the input coming from Bob's end can't really interact with each other. But if for the sake of argument, you did say, hey, let's just try to implement one, even though, if I open up the box, there is this hidden interaction going on between them, then yeah, you could implement it this way. For example, one trivial way to kind of think of it is to say, hey, whenever Alice and Bob get the input X in 0, 0, 0, 1, 1, 0, let Alice and Bob share the state 1 square root 2, 0, 0 plus 1, 1. But then if input is 1, 1, give the other entangled state to Alice and Bob, so that by definition, the correlations are exactly as we want it. Right? But obviously, to implement this physically, you need communication.
Okay, and would that kind of communication won't change the nature of the qubit themselves, like the qubit processing nature itself on bipartite state, the way they do it? So that won't be affected. That's what the condition is, yes, on the NLP.
So the condition is that if you're saying this, so the setup is kind of like before we know the value of X and Y, Alice and Bob already have shared the entangled state that you're interested in. Because they don't know the value of X and Y, so obviously they say, all right, let's share this one or let's share this one. But now the way we are defining how to get the non-local box correlation, the value of psi is dependent on, the value of X and Y. And so it requires an interaction between the qubits of Alice and Bob after or condition on the value of X and Y. And that's what violates the rule of the game in some sense.
Oh, okay. So got it. Okay. So before the X and Y generated, you should have this communication and then make it entangled with whatever the input is. Okay. Yeah, okay. Thank you. Got it.
No problem. All righty. So now we are coming kind of, I think all the background is covered. I'll just give you the juicy details of some recent results of our work in terms of how it connects to all that we've been talking about. So we know multipartite information principles are needed. And so that's what we did. We said, hey, all right, let's kind of play around with multipartite non-local boxes to see what we can learn about them. So there are a couple of results that I'll mention about them, and we'll finish by kind of bringing it back home to trivial communication complexity. So one trivial way to generalize, I shouldn't use trivial so much, one way to generalize the non-local boxes is to just kind of generalize the parity equals and rule, right? So you say, hey, there are n parties. So now the box will have n input bits coming in. There will be n output bits coming out. And the rule that this box will follow is that the parity of the n output bits equals the parity of the parity of the n output bits equals the and of the n input bits, right? And potentially you can even introduce noise into these correlations. For epsilon equal to 0, you can show that this would become the perfect version of the multipartite non-local box. And so you can play around with this. One question that people are interested in regarding non-local correlations is the strength of those non-local correlations. In terms of, well, if I wanted to simulate a given non-local correlation classically, communication becomes the key resource. So you can ask, if you have this non-local box with certain value, how much communication would the parties need in order to simulate that correlation? And that's nicely, can be nicely formulated as a simple linear program. So it's nice. We don't even need to go to semi-definite programs. So that's perhaps one nice thing about working in these non-local boxes versus if you do optimization over actual quantum stuff. Usually if you're doing optimization over quantum measurements or whatnot, you'll get a semi-definite optimization program or, worse still, a cone optimization program. Working with these non-local boxes, you end up with linear programs, right? So what we're doing over here is trying to say, hey, can we optimize the amount of communication needed to simulate a certain non-local box, right? So one observation that this is using is, imagine if you just go back to the base case of the two-party non-local box. If Alice were just to communicate her input bit to Bob, then obviously Bob knows both X and Y, and he can produce an output such that they will win the game. The same kind of idea now generalizes to three parties. If you've got Alice, Bob, and Charlie, Alice and Bob send their input to Charlie. And so Charlie is now able to generate an output such that the final output parity will satisfy the rules of the game, specifically this game. And so you see that if you've got an n-party game, n-1 bits of communication for sure are sufficient. We are not saying they are necessary. It might be possible to do it in less, but we are saying, for sure using n-1 bits of communication will do the job, right? And so that's the idea that we're using. Over here in this minimization of the objective function, we say, hey, with some probability, so PR over here refers to non-local box. So this is the probability with which an I-partite PR box will be used. And so an I-partite PR box can be simulated with I-1 bits of communication. And so if I sum over 2 till n, then I'm essentially saying, all right, consider all the 2 till n partite non-local boxes. The communication for an I-partite box requirement will be this. The probability with which it will be used is this, such that I'm able to find decomposition of the different PR boxes, non-local boxes that I have, and classical local deterministic strategies that I have, such that all of this expression on the left-hand side equals the box that I am interested in. right? So someone gives me this non-local box that I'm interested in, that is represented by this n, and I say, hey, I have access to some 2-partite, 3-partite, 4-partite non-local boxes. If it's an n-partite box, I have everything up till n-1 partite, because if you've got the n-partite box itself, then obviously there's nothing interesting to do. You just use that box. So you've got every kind of box up till n-1 partite, and you want to simulate an n-partite box. And so we want this equivalence. This bounds the amount of communication needed, and this is just the normalization constraint. Through linear programming, you can actually compute the dual of that as well. We won't go in the conversion details. A nice kind of observation to note, though, is this objective expression function value is actually what can be interpreted as the value of this Bell inequality, whereas the minimal the primal version objective function can be interpreted as the amount of communication needed. And so we then see, using kind of strong duality, that the amount of communication needed would actually end up being equal to the Bell inequality value of the game. So there's a direct correlation, direct link between, or equivalence, in fact, between the communication cost needed to simulate a correlation, a non-local box, and the value of that non-local box as well. Right, so I won't bore you with the details of solving this linear program, but what we are able to kind of then find is a protocol that simulates a given n-party box using at maximum n-1 party boxes. And the structure of the protocol is such that, if so imagine this is the local bound in the sense that if you consider this error parameter epsilon, if you make this error high enough such that the bound becomes equal to, for example, in the 2-party case, equal to 2. So in the 3-party case, 4-party case, it would be some other local bound. So the local bound over here in this plot represents the value of epsilon such that the box now can be simulated by just classical resources. If you lower epsilon, then that means you are now getting a non-local box. And if you make epsilon equal to 0, then this kind of is representing, I've got a perfect non-local box, and then on the vertical axis, you've got the amount of communication needed. And as we've argued, if you've got an n-party non-local box, n-1 bits are going to be sufficient to simulate it. Now, the trivial protocol would basically just say, hey, let's just take the convex combination of the perfect non-local box and the local bound, and you've got this line, and that will be the trivial communication protocol for simulating any box with an epsilon on this line, on this axis. What our protocol does, it identifies a structure which says, all right, if you start with the classical bound and now start decreasing epsilon, so you get a non-locality. Actually, because the non-locality is so weak in this case, you can actually now simulate this correlation just by a 2-partite non-local box rather than needing a multi-party n-party non-local box. And similarly, if you lower epsilon more, then from 2-party, you'll get to 3-party, to 4 parties, to 5 parties. And so you kind of identify these very specific deterministic cutoff points, such as those cutoff points identified by b sub k plus 1, etc. You'll be using exactly just the k-partite non-local box for simulation. And so here's some kind of simulation data of the results that we have. And so here, for example, for n equals 5, you note the dotted line represents the trivial protocol. Up this line is just a convex combination of local strategy, classical strategy, and just a 2-party non-local box. This square would just be the 2-party non-local box. Similarly, connecting this to this would be just a 3-party non-local box, and so on and so forth. Right? So we get kind of a communication protocol that does perform better than the trivial protocol. However, we can also numerically show that our protocol, which is this P, we have an analytic solution for this protocol. This protocol, even though it does a much better job than the trivial protocol, it's not exactly equal to the optimal protocol, and ends up being really difficult to get your hands on exactly what the optimal protocol would be. We have some numerical data on what the optimal protocol kind of behaves like, but we don't have an analytic solution for representing exactly what the optimal protocol would behave like. So that's all fine. But then based on this, when we were looking at these plots, we noted that, hey, we were minimizing the communication needed to simulate a given resource, but you can now also kind of flip around the problem and ask a slightly different question. Given the kind of resources that you have access to, what's the smallest epsilon you're able to find, right? So here we were saying, given a 2-party non-local box, this point will minimize the amount of communication. But perhaps it's possible to use the same two-party box with a higher probability, so it increases the amount of communication, but still using this two-party box, I'm able to lower the epsilon more. And so using a weaker resource, that is a two-party resource, I'm still able to get a smaller epsilon. So we can modify a linear program to now optimize the bound on epsilon rather than the amount of communication. And it ends up being actually a simpler linear program where you just say, hey, minimize this epsilon, the error kind of parameter in the parameterization of the non-local box, such that the noisy non-local box that I have equals to the convex combination of some non-local boxes that I have. Normalization constraints, etc. apply. And in our case, given the simpler nature of this linear program, we were actually able to consider a more general class of non-local box, multipartite non-local boxes. Remember, previously we had the parity of the output bits equals the AND of the input bits. Now we actually have what are known as threshold functions. So this represents the Hamming weight of the input bit string, which is just counting the number of ones in the input. And we are saying that the number of ones in the input string has to be less than some threshold level t. So the nice thing about this now is that when you're considering the structure of the Boolean function, rather than this 2 to the n possible different inputs, this constraint allows you to parameterize it in just terms of n plus 1 values, right? So the threshold could be 0, 1, 2, 3, 4, 5, 6, 7, 8, up till n. And the observation you can also make is that if I make the threshold equal to n for n parties, then this would be exactly the AND function. So the function flips to 1 exactly when all the bits are set to 1. Otherwise, the function is 0. And then you can kind of, the other extreme is not saying threshold is 0, but the interesting kind of threshold lies in the middle of the input. So if you set the threshold to n over 2, that's what's known as the majority function, right? Because if you flip it around, then it becomes symmetric if you're taking the less of majority versus the actual majority function. So the interesting thresholds are to consider are from n over 2 up till n, where we are making the observation that at n over 2, you've got the majority function, and at t equals n, you've got the AND function. And here's kind of the plot that we obtain for so the curve represents the optimal or the minimum epsilon attainable for a given threshold, right? So on the x-axis, you've got the threshold, and we have set n equal to 1,000. The asymptotic behavior kind of remains unchanged. And so if you look at this picture for a while, something non-trivial and interesting is happening over here, right? Before we had done this work, we would have assumed that this curve that we are getting would kind of have its maximum at exactly the threshold set to n over 2 for 500 in this case, because n is 1,000. But that's not what we observe. We observe that, you know, there's a maximum that occurs kind of slightly before n over 2. And then at n over 2, threshold equal to n over 2, we get this bound of 1 over 6. Now, as you know, that shouldn't mean much until we connect it to something that's already known regarding trivial communication complexity result. So this bound is 7n over 2 over 12, and this is 1 over 6. Right. So I just want you to keep that in mind, and we'll come back to this in the next slide. So what is this curve saying? This curve is saying that if you're using n minus 1 partite resources to simulate an n partite resource, a non-local resource, then the most difficult resource to simulate is not for threshold n over 2, but rather some threshold slightly kind of shifted away from that, asymptotically 7n over 12. Why should that matter? Because if you go back to the trivial communication complexity result, let me just remind people of the picture, and we'll conclude with this. So so there exists a result that says the trivial communication result that we kind of looked at, the deterministic version, the perfect version of it. The randomized version of it derives this bound over here, which is roughly 0.9. That result holds under the assumption or under the claim that it is possible to compute the non-local majority. Why should non-local majority raise a flag? Well, we said this threshold 500 is exactly the majority function. And this function should be computable with probability greater than 5 over 6. So if you can compute the probability, compute the non-local majority function with probability greater than 5/6, then Boolean functions have a specific property. And then using this lemma, they're able to show that a trivial communication complexity result holds for boxes that work with probability greater than 0.9. But we have seen in this plot that the hardest non-local majority, or the hardest threshold function to simulate, is not actually the majority one, it's slightly shifted away from it. And so that kind of raises kind of an interesting question, whether or not it's possible to close this gap between trivial communication complexities 0.9 and what's allowed by quantum mechanics. This gap over here. Could we potentially close this gap by moving to multipartite correlations? But now for those multipartite correlations, consider the communication complexity result not with the non-local majority function. I should have the picture in the same picture, in the same slide, not with the non-local majority with 5/6, but rather the threshold function that corresponds to this point. Because here we are getting data, and we are provably actually showing that this function is harder to simulate than the non-local majority. Then perhaps it would be possible to use that function. We get kind of a lower bound than this 5/6 over here. And so we get kind of a closer bound than this 0.9 probability for the result that claims that in a world where non-local boxes work with probability greater than 0.9, trivial communication complexity is possible. Ideally, what we'd like to be able to prove is that in a world where you can compute non-local threshold 7/12 with a certain probability corresponding to the previous picture, then this bound changes to 0.85. 0.85 is exactly the bound that exists for quantum correlations, right? And so that's then kind of the future direction we're interested in pursuing. And with that, I'll conclude my talk as well. And I'm happy to take any questions. Thank you for listening, and thank you for your patience.
Thank you, Jibran, for the nice talk. Yeah, so any questions from the audience, especially the students or the faculty for that matter?
I realize I should have had the references put in the slides. If you're interested, I can share the slides with the references put in after the talk.
Yeah, so a lot of this optimization is a bit kind of out of what we are familiar, like out of our comfort zone.
Understood.
So, as physicists, so yeah, someone with information theory background might have, so maybe you just want to give a context for the students here, like why this kind of the problem of non-locality in general, which arise in the philosophy of quantum mechanics. Yeah, what kind of why does it naturally lead to restriction on the information that can be on the information communication in a more general way, so to say? How can one describe it?
If you give me a couple of minutes, then I can kind of give, which in my perspective is kind of the foundational kind of reason in terms of the distinction between quantum and classical. So I won't go into the details of the additional talk I promised, but I'll just introduce this, my favorite example of quantum behavior, which is even kind of more foundational than this non-local, because this non-locality has this additional issue of requiring spatial separation between parties and no communication and whatnot. So something that brings more to limelight the key issue and doesn't even require entanglement is, now consider this. I have 9 variables. These 9 variables are physical quantities, right? So I label them A1, A2, A3, A4, A5. So imagine these 9 variables as something that I can measure in the lab. And I say, hey, can I find 9 variables that I can measure in the lab such that the parity, and I assume these are binary variables, so they'll take +1 and -1 value. So, just the binary experimental version. I the product of the entries of the three variables in each of the row is 1. So this A1 can be +1 -1, A2 can be +1 -1, A3 can be +1 -1. Same thing applies to all the 9 variables. But now I'm imposing additional constraints that each of the rows and each of the columns apart from column 3 has the condition that the AND of these 3 variables in the rows or columns is equal to 1. So that's essentially saying that the number of -1s that can appear have to be even, right? So A1 and A4 can be negative and A7 is positive. So then the product is positive. So that's all that I'm saying. Column 3 kind of flips it around. Column 3 says, hey, the parity of is negative. Can I find such 9 physical variables in the lab to measure such that these 6 constraints will be satisfied, right? So just like I was looking at A parity B equals X and Y, you can think of these now as 6 constraints that I want to enforce, 1 for each row, 1 for each column. And a very similar argument, just like we did for the A parity B equals X and Y game, would say, hey, let's assume, this takes +1 value, this takes +1 value, this takes +1 value. Then actually what I've computed is A1 and A2 and A3 and A4 and A5 and A6 and so on. And because all of these 3 are 1, the full product of these 9 variables also has to equal 1. Whereas if I take the 3 constraints of the columns, then I'm saying A1 times A4 times A7 has to be 1, times A2 times A5 times A8, which has to be 1, but times A3 times A6 times A9, which has to be -1. So the product of the 9 entries, again, if I do it based on the column constraints, has to be -1. And so here I get again kind of that complementary kind of conclusion that the product of these 9 variables row-wise constraints has to be 1, with column-wise constraints has to be -1. And so what's up? This classically allows us to conclude that there exists no deterministic satisfying assignment to these 9 variables which satisfies these 6 constraints. Quantum mechanically, the solution is trivial. You just have these polymatrices, and it's a nice simple exercise to verify that the expected value of each of the rows and columns is +1 because the product of these entries is identity, 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 except for column 3, which is minus identity. So the expected value satisfies the required constraint. So now, why is quantum able to pull off this trick while classically we just concluded we couldn't? Because classically we were asking for a simultaneous satisfaction of of a value to all of these 9 variables. Stated another way, which I like in terms of probability theory, you're asking for a joint distribution to exist over the 9 variables. You're asking for this mathematical object to exist, P of A1, comma A2, up till A9. You're asking for this joint distribution to exist while satisfying certain correlation constraints on the subsets of these random variables. Whereas the quantum solution pulls off this trick by basically saying, hey, in the version of the game, you say, hey, I will check whether or not the constraints are satisfied by basically checking any row or column constraint at any given time. Now that becomes brings in the interesting philosophical constraint, right? Quantum mechanics, with its issue of anti-commutativity, says that only observables that commute can be simultaneously measured. So you already see that, let's say entries in the diagonal can't be simultaneously measured. And so quantum mechanics in its our mathematical formulation of quantum mechanics brings with it a certain restriction that says, hey, this joint distribution property, don't ask me for it. So even quantum mechanics is also not saying that, hey, this joint distribution will exist, because quantum mechanically it's saying, I will not even allow you to ask the question of all the 9 variables simultaneously. But if you ask me about any single row, any single column at any given time, I will give you a satisfying answer that satisfies your constraints. And so the issue becomes now this reconciliation of, even though quantum is somehow restricting your ability to define this joint distribution, yet it allows for the satisfactory assignment or satisfaction of these 6 constraints. How do we understand this? Historically, people have called this, one way to think about it is realism, that classically we were saying, hey, all these physical variables have some determined value, even though if we don't know it. Whereas quantum mechanically, we are saying, in the words of Asher Perez, unperformed, which I'm kind of summarizing, unperformed measurements don't have any result, right? So if I didn't perform the measurements corresponding to row 2, it is not reasonable for me to ask, well, what would have been the measurement result for row 2? And so those results don't exist. And that's the key departure from, I think, our classical intuition there, that unperformed measurements don't have a result, whereas, or philosophically, does the moon exist if no one looks at it? Does the tree in a forest make a sound if no one is there to hear it? Quantum is kind of going along those lines. We're saying if you didn't perform a certain measurement, don't ask me about the value of those corresponding observables. And I think for sure, I think this is an issue that people, established physicists, still would take an issue with. There, I think within the literature, you'll find what's called today cubism. Christopher Fuchs have a bunch of great email exchanges that he has put on the archive, where he has kind of developed this model of cubism, where you really kind of think about the world really as just Bayesian probability updates, and there is no inherent reality. And kind of on the other extreme, you will have multi-world interpretations or other variations thereof, where you can force a realist interpretation on this setup at the expense of some other kind of weird kind of gimmick, right? So you say, hey, there's multiple universes, or you say there are these hidden local variables, etc., etc., etc. So for sure, we don't have the time to perhaps go in the detail of all those different possibilities. I think the key takeaway regarding all of this from the quantum information side has been that rather than getting into a dogmatic debate about which interpretation and which way of looking at it is right, really treat all of these approaches, interpretations as possible ways to get a different perspective on quantum information, on your ability to compute information. And so if for a given task, a certain perspective of quantum information helps you, quantum mechanics helps you for doing a certain computation, go ahead and use it. So be more pragmatic rather than philosophical.
But do these different philosophical approaches result into different correlations there?
No. Right. So all of them are going to be doing the same experimental result. It's just that the underlying interpretation of, well, what's actually going on so far is different, right? So none of them, because if one of them, okay, let me kind of rephrase that. So when we were talking about these non-local picture, here, right? So there have been papers where people have talked, so this bound is what you would call the limit on what's allowed quantum mechanically. There are correlations called almost quantum, where people have said, well, what if we considered like an epsilon perturbation that puts the correlation above the quantum bound? And so that's an almost quantum correlation. Could they exist in reality? And so people, and now I'm out of my comfort zone, people have looked at kind of cosmological setups near black holes and whatnot, and try to argue, why such exotic situations might allow for something that violates this quantum bound. But so far, all the generally accepted interpretations of quantum, I think all agree upon kind of the experimental behavior, right? It's just the interpretation that they differ over.
Okay, yeah. So yeah, okay. So what's happening when we are not seeing is yeah. Okay. Adam, you want to say something? Yeah, thank you. Thanks a lot for this explanation.
Thank you, Jibran. I
would just say that long time no see.
I would just say for the students, it might be easier to understand all this if you give some physical system to implement all this. So, for example, when you're talking about, you could talk, for example, about photons. ये आप सारी scheme के photons के context में कैसे implement करोगे? Some physical setup.
Right.
So, if you can just quickly sketch out for the students that physically आप ये किस तरह सब कुछ करोगे?
Imagine if I wanted to implement this hypothetical non-local box. Imagine there's this monkey sitting inside this box that actually receives this x and y as input, and whenever xy is this one of these three values, outputs this entangled state. And if xy is equal to 1, 1, then outputs this entangled state. Right. So this, so the issue over here is if Alice and Bob were not able, or if this coming together of x and y was not possible, then this conditioned swapping from this psi to psi prime would not have been possible. And so that's why it's not physically realizable while satisfying the no-ceiling conditions. But if you were to say, hey, let us try to come up with some kind of physical realization with a monkey inside the box, then a simple setup which does that realization is to say, hey, the monkey sees if xy is one of these three values, produce this entangled state. If xy is 1, 1, then produce this entangled state. And now Alice and Bob don't have to do anything interesting, just perform a measurement in computational basis measurement, and you'll get correlations that exactly produce these correlations. Yes, you can simply just verify that by inspection. Right. On input 0, 0, 0, 1, 1, 0, I'll get an even parity output. On input 1, 1, I'll get an odd parity output between Alice and Bob with uniform probability.
Right.
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 Yeah. So, anyone else have questions?
If anyone's interested in following up in any of one of these questions, more details, or follow up on this research direction, please just drop me an email and I'm more than happy to follow up.
Okay, Jibran, maybe it's because a lot of these topics are pretty kind of unexplored by students themselves. So can you maybe recommend like a literature or some nice book or review paper where they can start reading about it, or that can be a starting?
Would it be okay if I send it over email? And I'll
share
a couple of links.
Sure.
Right. Okay.
Yes.
Yeah, sure. I'll do that.
That would be great. Yes. Yeah.
So I'll do that right now.
Okay, great. Yeah, the idea of these colloquia, like just to get them introduced to new,
I think it's wonderful. Yeah, I think that's great.
It's not just the introduce it, just कि at least उनको नाम कोई पता चल जाए कि different topics क्या है.
Yes.
Right. No, I mean. सही है. Yeah, but this was nice कि चलो थोड़ा सा ज़्यादा computer science, ज़्यादा information theory की I think अभी तक talk नहीं हुई थी.
Yeah.
अच्छा. Very nice.
Yeah, I don't know if we do have in our CS department people who are interested in such problems.
So I recall a couple of years back when I gave a talk, there wasn't anyone, but I'm not sure whether that has changed since.
वो जो अशर है, I think maths में, I think he works on quantum graphs.
Okay.
वो थोड़ा बहुत इसे मिलता जुलता है, थोड़ा बहुत. But other than that, no. I don't think so.
By the way, Adam, would it be okay if I disturb you some point later, perhaps about some of the activities we've been doing with Q Pakistan, and if we could?
Yeah, of course.
Sure.
Most welcome. Most welcome.
And Ata, you as well. You know, it would be great to have both of you involved with that.
Yeah, sure. Yeah.
Excellent.
Yes. So you have this kind of a society or whatever you want to Q Pakistan. Yes. So for students who don't know, maybe you can introduce it a bit. What it
right. And so I'll share some of the details. It's been the global version of it has been quite active, especially this semester. So I was thinking, you know, connecting more to that global initiative might be useful for us locally as well.
Yeah, sure. Yes. Okay. So then, so if there are no other questions, then I would like to thank Jibran again for such a nice talk and introducing us to this very exciting aspect of the confluence of quantum mechanics and information theory. So yeah, thank you, Jibran, again for this. Thank you all for joining in this session. Yeah. So the recording, so Jibran, ek cheez main aapse bhul gaya tha start mein. So we were recording this session, so I hope you don't mind. But in future, yes, we might share it on our
Sure.
channel, on our YouTube channel. So
Right, sounds good.
yeah, okay, yeah, great. Okay, thank you all. So for the
Bye.
Hafiz. Yeah.
Allah Hafiz. Bye bye.